So welcome to the lecture. I wish to start with some announcements again. So there's a tutorial session with Evgeny later today after the lecture. And I got a feedback from the feedback last week or 2 weeks ago that they wish to have more interactive elements. I guess to make sure that everyone is following the lecture. So I'll try to be kind of waiting for questions after each meaningful sections and try a bit harder to make sure that everyone is following the course, okay? So let's continue with the feature attribution. I actually wish to revisit the LIME framework that we talked about last week to give better intuition. I realized that that was a little too quick towards the end of the lecture, so yeah, so we are looking at the case where missingness is well defined. And that's typically the case when you have a language model, for example. So you can just delete a word or something, and then there's no limitation of like you should fill in all the entries of a fixed size input, like in images, right? Images have a very fixed, very rigid kind of dimensionality as an input. So if you wish to remove some information there, you actually have to fill in those pixels with some information. But for languages, you can just delete it and that's fine. And typically there's a token assigned for missing values like mask token M, right? So what happens if you give some natural language input to, let's say, a language model, is that the model should always take some fixed length input anyways, right? Because it's a parametric model, so it has to know like how to deal with a fixed size tensor instead of some varying size, or at least there should be some kind of upper limit on how much length it can take care of. But what's special about language model is that it has this special token called mask token, right? And then it knows what to do with those mask tokens. It treats the mask token as kind of no information. So if you have a shorter than kind of window size input to a language model, then it basically pads all these mask tokens for the location of the sentence or outside of the sentence, such a way that you are actually completing the sequence for the model to process the input. So yeah, in text domains, you typically have no issues with missingness because there's a designated token for that. So let's take a look at kind of language model or text classification task here. So you wish to tell if a given sentence is a spam reply on your YouTube channel. And for that, you wish to use your machine learning model, but also you want to find out which features are contributing most to, or which words are contributing most to the prediction. So there's one positive class or negative class in this case, Sai is a good guy, and one positive class saying for Christmas song, visit my channel. So the second example is actually a positive class for spam because it's asking you to visit your channel to view the videos and increase their profit. So here the input of interest is for Christmas song, visit my channel. And there are features like for Christmas song, visit my channel, and then smiley face. So your question is which word is contributing the most? And to find this out, what you can do is you can erase some subset of features at a time and then take a look at what's the response of the model. How does the spam likelihood prediction change? So for example, if you're removing 4 here, your spam prediction, spam likelihood is 5% point less. Whereas if you erase channel here, your spam prediction is 24% points less, okay? So from this, we intuitively know that some of these words are more kind of critical for the spam prediction, while the others are not. But how do you really do this in a more systematic way, right? And for that, actually before that, I wish to kind of make a parallel between this and input gradient before. So this is the diagram for input gradient, if you remember it. And in this case, we're doing a kind of discrete version of the input gradient, right? Because the input domain is not continuous anymore, it's not pixels, so you cannot change values by an infinitesimal amount. Instead, you can erase one word at a time. One word is probably the smallest kind of metric here for measuring the change of input, right? So in this case, I call it feature I, right? And then we can take a look at the counterfactual case when you remove this feature I and then see the response from the model. Okay, so it's kind of trying to be very similar to input gradient, but there's fundamental limitation, but still you're trying your best here. Okay. And I wish to take a look at this in a more systematic way. And you know, the other perspective for input gradient is you're basically fitting a linear model, a tangent model at that test point, right? Basically linearizing your model around some point. So you wish to do something kind of similar here, right? So for that, we need some numeric input, right? If you wish to apply some linear model, then you need some numeric input to start with. And actually for discrete models, it's always possible to have more discretized representation. So, or binary representation. So each location in your binarized input indicates the presence of a word, okay? So it's not necessarily indicating the sequence ordering, it's more indicating the presence and absence of each word, okay? So the first entry is indicating the presence of 4, the second Christmas, etc. Okay. So you can turn this discrete input into binary input, and now you have the original span likelihood, right? And between these binary features and the span likelihood, you can fit a linear model. That's what you're trying to do here. So I'm taking this affine linear function, beta node plus beta 1, z1, etc. By the way, z is the binarized version of the original input x. Okay, I'm missing a beta node here. Okay. So given this kind of binarized input, what you're going to have here is beta node plus beta 1 plus beta 2 plus up to beta 7, right? And then for that, you're going to have span likelihood of 99%. And here, in this case, you're missing beta 1, right, in your summation. And then you have 0.94 as the likelihood. How to figure out the weight here? It's fairly simple if you have just these two cases, right? You subtract this from the above and you end up with beta 1, right? And that corresponds to the difference between these two, and that's 5%, 0.05. So in a sense, if you just consider this case, we have the same intuition as before. To look at the contribution of a single word, you need to just consider two cases with the full sentence and with the sentence without that word, and then take the difference. But you know, like there are not just cases where you can erase single words, but also you can erase multiple words, like in this case. If you erase Christmas and channel together, then you have a different number here. And sometimes, well, in many cases, they make clashes. So if you're estimating beta 1 up to beta node up to beta d with just single word erasing, then they may not correspond to erasing, in this case, beta 2 and beta 6, right? It's not linear, right? Yeah, how can you see that? So from here, we know that beta 1 should be 5%. Yeah, and from the comparison between this and this, you know that the contribution of beta 6 should be 0.24, right? But they don't actually add up to, right? Um, so in this case, it should be, the summation should be 30, but it's not exactly 30, right? It's close to 30, but it's 29, right? So there are some inconsistencies. How to take care of that? And for that, we try to fit a linear function, right? So we assume that there should be some noise, right, in your likelihood. And what you do in that case is fit a linear regression model, right? So you have this target, which is given by the original function f, and you introduce this linear function. And the objective for beta is such that the difference, the error term, is as small as possible in terms of the L2 distance. So, but here, we are not just fitting the linear model, but still we wish to focus more on the cases where the change from the original input is not so great. So we put some weight term here to indicate that we are more interested in small changes from the from the original input. And one could use a RBF kernel like this one. So your kind of tail is going exponentially small. But of course, you can also dictate this weight to be kind of 1 for every single word changes, okay? And then you're actually just looking at the predictions where your single word changes from your original input. And then you're actually recovering the original formulation where you're connecting beta 1 up to beta 7 to the erasure of removal of single word at a time. So this formulation is slightly more general than that case, right? We wish to still account for the case where you can actually erase more than one word, right, at a time. So it's nice continuous relaxation of that. And finally, the other nice characteristic of this formulation is that you can put whatever regularizer you want. And when it comes to explainability, it's super important to have a small number of features cited, right? Otherwise, you may find it super hard to understand what is the real contributing factor here, right? If the model is showing you like 100 different words, then how can you figure out, yeah, which ones are actually contributing? So what you can do here is to make the linear model sparse. So for most of the beta entries, the value will be 0. And you can only take a look at the entries where the value is non-zero. Okay, and you can control the strength of this regularization by controlling this lambda here. This is a version of lasso regression, if you know what lasso is. And this is exactly what Lime is doing, right? So I wish to kind of make a connection to input gradients and Lime here. So sort of Lime is inevitable kind of relaxation of the input gradient when the input space is discrete, okay? So there's no real magic here. It's just another way to linearize the model around some test point. Yes? So you're wondering whether, sorry, I didn't get your question, sorry. Yeah. So you're questioning how to set the weights in this case with Lime or in other cases? So, well, basically solving this optimization problem will give you beta values, right? Oh, the W, okay. So these weights here. Um, okay, so that's a very tricky question because yes, there's no single answer to this. Um, as I said, one could use um, the discrete the binary space as the space where you compute the distance, for example, right? So in this case, we have the distance between this one and this one, which is 1. Um, between this and this, you have distance 1. Yeah. Between this and the original, you have distance 2, right? And they could be, yeah, so sometimes this minus and L2 norm is not well defined, right? Because it's discrete space. But what you can do here is compute the distance in the binarized space, for example. It's also called Hamming distance. And then you can do exponentiation on top of that to make it more dramatic. Um, you're favoring like one distance um, samples much more than, let's say, two distance samples, for example. So that's one option. But of course, the critical dispute around Lime is always how to set the weights here. How do you actually define what is local, right? So there are some pros and cons. If you set the local as way too restricted area, then um, it just boils down to just looking at erasing single word at a time, right? But if you set it too broadly, then there's some decrease in faithfulness or soundness. So basically, your explanation is telling you which words are actually important, but they are probably not what the model is actually doing. If you refer to too many, try to explain too many points in the space, because like this is highly nonlinear function. So if you wish to put a linear function that's approximating um, a large range of regions, right? Which is defining a highly nonlinear function with so many ups and downs in the function, and you try to fit a linear function on top of that, then you're gonna miss a lot of variations that are interesting for the model. So yeah, there's no quick answer to this, but people consider different options here. Um, one option is just to measure the Hamming distance, for example. Yeah. So I think the benefit of this weight is more evident when you have a longer text, for example. And let's say it's a whole document, right? And sometimes you don't want to. So if it's a whole document, right? Um, then your binarized input is not. Binarized input is basically a counting of how many words are there for each word, for example. And so sometimes you wish to look at the contribution of a sentence, let's say. So forget about what I said about the counting. So let's say the document is super long and you wish to kind of know the contribution of a sentence, for example. And then that's not a single word anymore. And so you need to have a good understanding of what's going to happen if you have a set of words erased. Okay, and in that case, what you can do is um, since you have a linear model now, you can estimate the prediction when you erase a set of words. So you're going to have a different binary. So in this case, let's say this single word here is instead a single sentence, right? So I'm not making a good example anymore. So let's say you're interested in the case when you erase actually these two words, okay, in your document. And then you wish to have a good estimate of this 0.70 instead of having to do the prediction on this particular sample again, right? And then that's going to give me a rough estimate of what's going to happen in that case. For this linear model to model these kind of multi-word erasure cases as well, you also need to kind of fit the model on these cases as well. And that's why you're not just looking at a single word erasure, but also multiple erasing of features here. I think it becomes more frequent when you have a longer documentation and longer input sequences. Okay. So here's some example. It's also useful for tabular data, which is also a discrete case. So let's say a person has diabetes with 72% likelihood, and you can break down the contributing factors to diabetes diagnosis here according to different features. And these features are given by the contributing amount from this sparse linear model. Okay. So for many of the entries will be 0, and there will be a few entries which are non-zero. And so it's kind of easy for humans to know for this person in particular what are the contributing factors. Okay. So far, any more questions? Otherwise, I'm moving on. Okay. So let's take a look at Shapley values. I'm going to take a look at a different input here, gloomy intense yet profoundly inspiring. I could have used the same example here, but I just wanted to give another type of example here. So here the question is, how much does the word inspiring contribute to the positivity of the sentence? So the task here is to tell the sentiment of the sentence. Let's say this is a movie critic, right? So this is a little bit confusing sentence, but still a positive sentiment, right? Because eventually it's saying inspiring, right? So there are two ways of looking at this. So one is sort of input gradient-like approach, as we've done with line, but there is also integrated gradients way of approaching this problem, which is Shapley values. Okay. So what did you do for integrated gradients? You first set a kind of global change inside the input space. And then along this change, you take a look at the deltas along the line. And you kind of sum up the changes introduced by this delta along the way, where the deltas are kind of always in the same direction, to the feature ith direction, okay? So you're basically integrating the gradients along this line segment, where the gradient is towards the ith feature. And you can do something similar here for discrete case. So your starting point is x, and x has feature I, right? And we can change from this input x to a null input where you do not have anything except for I, right? Okay, because you need to take the difference between the case you have I in your input and the case when you don't have I in the input. So, you know, like for line, we are primarily focusing on this case in particular. So the original input and the case when you don't have a feature I. But we are interested in more global changes or global contribution of feature I to the prediction. So yeah, the most extreme case is when you have feature I alone, and the case when you don't have any feature at all, when your input is just a null feature. Okay, but all the cases in between are also our interest as well. So we're considering subsets where the subset contains feature I, and we wish to take the difference between this subset Z and the case when you don't have I in the subset. Okay, so and in each case you're going to take the difference, and you're basically going to average the difference in the model prediction along this line. Well, actually, it's not a line anymore, because the way you decrease from your original set to null set is not uniform path, but there are several different paths of doing that. So yeah, so if you sum this up, then you can write it down like this. You take the expectation over all subsets of x, which is containing I, and you take the difference between the model prediction on Z minus prediction on Z minus I. And actually here the expectation is not uniform across all possible subsets containing I, but it's actually, it has some stages. So you're first taking a uniform sample for the subset size, and then given that subset size, you're doing another uniform sampling among the subsets. The reason why they do this is because I think it has better theoretical characteristics. I think if you just sample at random uniformly from all subset sizes, then all possible subsets, then you probably don't have good theoretical characteristic that I'm also going to introduce at the end. So in practice, how you compute this is as follows. You do a weighted summation, right? Where the weight is defined by this, this value here. So one over size of x is coming from the fact that you're doing uniform sampling. So for every subset of size m, which is a value from this set, it's going to have the probability of being picked up, which is 1 over the size of x, okay? And for every subset, the probability of that subset being selected from this all subsets of size n is 1 over the number of possible subsets that is of size m and contains feature I, okay? So this is basically counting the number of possibilities for selecting a subset of size m, well, size z in this case actually, and containing I, right? So how do you compute this, right? To compute this possibility, what you do is, yeah, you first have a size of original feature, which is m, this size of x, right? And then I is assumed to be kind of chosen by this subset. So we take I out, okay? And then for for the subset of size n, we need to assign m minus 1 different values for the other elements than feature I. So we just need to assign m minus 1 entries from the possibilities of x minus 1. And that's exactly x minus 1, choose m minus 1 possibilities, and that's basically plugged in here, okay? And if you kind of expand this, then you have this kind of, factorial expression, okay? And in practice, how you compute this is something like this. So when the input is gloomy, tense, yet profoundly inspiring, you consider all possible decomposition or kind of all possible subsets containing the word inspiring. So you're going to have gloomy, tense, yet profoundly inspiring, which is the original. And you're also going to have gloomy, tense, yet inspiring, or tense, yet inspiring. And also eventually you're going to have a sequence with just inspiring, right? And for each case, you're going to compute the positivity of the sentence. And you also consider cases for each possibility here when that inspiring word is missing. And you're going to compute the positivity again. And you can take the weighted average across all these possibilities here and do the same weighted average across all these possibilities here. And that's going to give me 71% on the one side or 21% on the other side. And if you take the subtraction there, which gives you 0.5, that's exactly what Shapley value gives you for the importance of the words inspiring. So the weights are exactly based on this formulation here. So you're doing kind of expectation, right? Which is weighted averaging. Okay, everything is clear so far? Okay. So the theoretically nice property that I mentioned about, which is necessitating this weird way of taking the expectation, is all because of this completeness axiom, so-called, right? So for integrated gradients, we had a nice property that you can basically decompose the difference between the the current prediction for this particular test case versus the prediction for the base input as a summation over all attributions over the features. Okay, so we had that before here for the integrated gradients, but now we have the same kind of argument for Shapley values. So if you take the difference between the current output for the model and the output for the base input, that decomposes into the contributions from each feature, okay, as a summation. And now this is super easy for humans to understand because humans are good at understanding what summation does, right? Yeah, so that's kind of nice. And that's it for Shapley values, okay? So I like to summarize the feature attribution part in this way with this kind of, well, there's actually one more topic, but so far we've looked into basically two different paradigms here. So one is making small changes from the test input and see how the model responds to it. And on the other case, we also had cases where you're erasing every single feature from the given input until you're left with nothing, like you're missing all the features. And see how much each feature contributes to the prediction for the current sample on the way. So on the local perturbation side, you have input gradient, smooth grad, and line for discrete inputs. And on the right side, we had integrated gradients and Shapley values. Shapley is kind of, yeah, some add-on on top of Shapley values. I mistook, yeah, it should be Shapley values here. There are some pros and cons here. So if you're just looking at the local perturbations, yeah, it's, I would say, well understood properties. So yeah, I wish to actually raise this because, yeah, what do you mean by that? I wish to emphasize more the independence from the reference values, which is a super good feature here. But the con is, of course, that you're only looking at infinitesimal counterfactuals. Who is interested in erasing a single pixel, for example? Well, for discrete inputs, probably it makes more sense because you're actually not changing infinitesimal amount at a time. But still. And if you're looking at global perturbations, your counterfactual is indeed beyond infinitesimal changes. But here, what's not clear is how to set the reference value, how to define what is missing, okay? And it also tends to be a bit more expensive. Okay, so that was it for explaining the whole model, but for around specific test case. And now we also wish to look at the other cases. So, okay, so this is what we've done so far. So we have a complex model like, yeah, I have this here two-layer neural network, but think of this as a, yeah, deeper model, for example. And there's model and there's input domain. And yeah, this is sort of a complex model that we wish to understand. We're given a test sample of interest, X, in the input domain. So what we've been doing so far is we wish to explain the whole model, G and H together, but around the test input of interest. Okay, so input gradient is basically trying to linearize the function around this X. So f of y is equal to f of x plus the difference between y and x times the gradient, okay? This is just gradient formulation, but there is a small o of y minus x term, so if your y is deviating too much from the test case of interest, then this linearization does not work anymore. For integrated gradients, we also had a linear formulation. So f of x is decomposed into some base term here plus some feature-wise contributions. For line as well, yeah, this is basically a summation of individual contributions plus some intercept here. Shapley value is also linearizing the model, right? As a summation between the base case prediction plus some feature-wise contributions here. Okay, well, actually, there's a summation over I missing here. Sorry about that. So these are all trying to linearize the model at some point in space for the whole model. But the other possibility is to explain only part of the model, right? But by doing that, you're actually explaining the whole input region, okay? So it's not really possible to explain the whole model and explain the whole region at the same time, because then you're not faithful anymore. The model is very complex, and the model is defined on a vast range of inputs. So if you're trying to linearize the whole thing, the whole model on whole possible inputs, then you're introducing a lot of errors, and your model is not the same as before. But by sacrificing a little bit from each side, either the part of the model or part of the part of the input space, you can actually explain it better. So let's take a look at the other case. Right? You try to explain everything, but only for a partial side of the model. So in this particular case, we look into the case when this h of x is actually linear. And so humans do understand h of x quite well. And we don't care about g of x. Yeah. That is actually the case for CAM, class activation mapping. So yeah, basically I wish to kind of explain what that is. But this is kind of a simple diagram showing what convolutional neural networks are generally doing with some caveats. Okay, so given image, there's a model which is going to produce some score map over the spatial dimensions. Of course, there will be a lot of channels as well. And then there's going to be some linear function, in this case, spatial pooling. And then finally, there's a class label predicted. Okay, so this is a very simplified view of what these models are doing. And actually, if you look closely, actually none of the existing models are exactly doing this. But still, I wish to make this a reference case where things are super working well. Okay, because now the spatial pooling is basically just doing average, unweighted average across all the spatial locations here. And so for humans, it's very easy to understand. And you can even draw a heat map, because now this is an image domain. So if you ask, if a user asks which pixels contribute to cat prediction, then we can show heat map like this one, and then say, yeah, the red parts are actually contributing most to the prediction of cat. Yeah. But for this to work, we need some key requirements, right? First of all, h needs to be linear, right? I'm not mentioning that here, but it was mentioned in the previous slide. And for this linear model, the inputs and outputs should be kind of making sense to humans, interpretable, okay? For example, in this case, the score map is kind of interpretable to humans, right? So it's good. The outputs of h should be also interpretable, meaning that it should be kind of semantic class, for example, like cat. The other question is whether that applies to a wide range of model classes. So CNNs, for example, it generally works in many cases. But what about transformers? Is it also going to work for transformers? not so clear. So we're going to answer these questions here. So when H is a summation over a feature map, yeah, I said it's now a good case, right? Because yeah, your final score is a summation, and you can rank pixels. So let's take a look at individual architectures at a time and see whether the requirements are met. So let's take a look at AlexNet. I hope you also know AlexNet. It's basically the first working convolutional neural network. And it was so simple that you can actually write down the full configuration in this table. Nowadays, it's not possible in general. And the way you read it is basically you have some inputs here for every row is a layer. And for every row, you're going to see the input dimensions and output dimensions. And the name of the layer, as well as the operation here. So every operation is some variation of convolution or linear mapping. So you have some stride, padding, kernel size, and input channels and output channels, and number of parameters here. We don't need to look at all this configuration. We just need to look at the final output, the final feature map dimensions, and what follows afterwards. Because feature map is the signal that we understand. It basically assigns values to different locations in the image. And if you actually go beyond the feature map to just feature vector, then we lose understanding of which pixels are contributing how much to the prediction. So this is sort of the last layer where we understand the pixel-wise contribution. And the dimension here is 6 by 6 by 256. And then there will be 3 more layers that follows afterwards. So you're doing some flattening here. So you're turning 6 by 6 by 256 into a huge dimensional vector by flattening it out. And then, yeah, it's close to 9,000 dimensions. And then you're doing this 9,000 times 4,000 matrix multiplication on top of that, and then put a ReLU function, and then do something similar on top and do it again. And then finally you have 1,000 dimensional prediction. If you define this feature as the input to your H part, right, which is supposed to be linear, then H is actually not linear because FC8 is a linear layer, but FC7 and 6, they contain ReLU, nonlinear activation. So as a whole, this is not linear. So for AlexNet, we cannot do much. Yeah, and also the other caveat is that if you have 256 channels, each of the channel dimensions are not fully interpretable to humans. So you kind of know that there's some segregation of information to different 256 channels, but yeah, you don't basically know how to make use of that. For VGG as well, the final feature map is 7 by 7 by 512. This in itself is not interpretable because 512 channels are not containing intrinsic meaning. The other problem is that there are a sequence of linear layers on top, which makes it nonlinear. Yeah, I mean, because of the ReLU activation. But now, let's take a look at GoogleNet. The final feature map dimension is 7 by 7 by 1024. Again, the problem is that, actually it should be 1024. These channels do not encode any intrinsic meaning. But now what follows afterwards is actually fully linear because the average pooling is linear. It's just a summation. An FC layer is a linear layer. There is no ReLU on top because you need to make a prediction afterwards to 1,000 ImageNet classes. So yeah, if you compose a linear function with another linear function, then it's still linear. So H is finally linear. And the only problem is that these 1024 dimensions are not interpretable. But what class activation mapping did was to turn these 1024 dimensions into a linear into an interpretable 1,000 classes of ImageNet, okay, using some trick, which I'm going to talk about. Let's take a look at ResNet as well. So here, again, the final feature map is 7 by 7 by 512. Well, it depends on the on the exact architecture in the ResNet family. Sometimes it's 1024. It doesn't matter. Again, the 512 is not interpretable, but there's a way to turn this into interpretable as long as the layers that follow are eventually linear. So again, here's average pooling and fully connected layer, which is completely linear. So it's good. So how do you turn these dimensions, 512 or 1024 dimensions, into something that is interpretable? And yeah. So this is kind of visualizing what ResNet is doing, for example. So you have a sequence of convolutional layers, and you have some global average pooling, and then you do some FC layer here, which is doing basically for each feature here, you're multiplying that with some weight here in order to make the prediction for this particular class of interest. Okay, so I like to write down each tensor involved as with the index notation, because otherwise I really hate this kind of notation here, because you don't know how many dimensions there are and so on. So I always use this kind of index-based notation. So I wish to write down the final feature map here as FLHW, where L is indicating the channel dimension and HW are spatial dimensions. So yeah, so L is from 1 to 512, and H and W are from 1 to 7, right? And based on that, you do a multiplication with W, which is a matrix, of dimension 1000 times 512, right? So L is the same channel dimension as here, and Y hat is the particular class of interest. So in this case, Australian terrier. So in this, if you write it like this with the hat, then it's not a matrix anymore, but it's a slice of the matrix corresponding to Australian terrier. And if you have this kind of vector, which is indexed by L, and if you have a tensor, three-dimensional tensor, you can do dot product between these two for every location HW, and that's going to give you actually you have to do global average pooling first, right? So you're going to end up with just a free index L here afterwards, and then you're multiplying this vector with this vector here to end up with the score for Australian terrier. I hope that's clear. So you're doing global average pooling here across H and W dimensions, and then you're doing matrix multiplication with YL, WYL here, to end up with a vector indicating the scores, logit values for every class. Yeah, this is convolutional neural network. And then you do softmax, of course, to compute the likelihood, probabilistic likelihood. And if you like to train this one, then you put minus log in front, and then you only take a look at the ground truth class and just train it. Okay, so that's just describing what the convolutional neural network is doing. And here, what's happening down here is how you explain it. So you have feature map. So this is a channel-wise feature map. So this is the case when L is 1, L is 2, L is 3, and these are all F bars, right? When L is right, and L is 512. And then you're summing over these individual feature maps according to some weighted average, where the weights are coming from this matrix here. So we know for Australian terrier and for L equals to 1, what should be the value of this weight, okay? And we are basically linearly combining all these feature maps. And then that ends up with some feature map that is meaningful for you who are interested in Australian area, and that's explaining exactly from which feature location the biggest contribution comes. And if you write it down like in mathematical formulation, you have something like this. So you have the feature map, and you take the so this is a vector, right, with the free index L, and you're basically taking the dot product for every location in the feature map to get eventually a final feature map that tells you the contribution. Okay, ready to get started again? So let's take a look at how to simplify the CAM formulation, because you know, like maybe depending on the perspective, you may think the formulation already is quite nice and quite simple, but we actually found some time ago that there are some possible simplification of CAM formulation. I mean, code-wise. So yeah, let's take a look at what I mean by that. So as I said, a likelihood like this, where we have FC layer followed by global average pooling. So, but now let's take a look at this this FC layer and the global average pooling, right? It turns out that you can actually swap the operations because these are linear, right? So you can take this summation over I and multiplication with, sorry, summation over L and multiplication with WYL inside the inner summation, and that's going to give you something like this. And here we can define the inner summation and multiplication as a new feature map that's given by FYHW. Okay, so each Y is basically the result of doing the dot product between WYL and FLHW, where L is the running index. And if you write it this way, then eventually what you have is you have this kind of feature map, and you just do summation, global average pooling, and then softmax. So this is a nice formulation where you do you have the feature map followed by global average pooling, and then you do softmax. It's the same formulation here and here. It's just that how you compute things in different order. But if you write it down like this, it's very simple. Like, yeah, it's more pleasing, right? Rather than writing this, you can write it like this. So you can say you're training this function. What is even nicer is that for explanation, right? Before you had to do this computation, right? For this uninterpretable feature map f bar, you have to do the weighted summation over all different channels in order to generate an interpretable feature map, right? That's what CAM does. But if you formulate this way, what you can do is you can just slice the ground truth class y hat out from this feature map, and that's it. So yeah, if you formulate your network this way, then what CAM does is exactly just taking out the channel of interest from this feature map. By the way, this feature map has now a dimension 1,000 times 7 by 7. So each channel dimension is has some meaning corresponding to each ImageNet class. Okay. Since this is a little bit confusing, and yeah, some people may find it hard to understand what I exactly mean by that and why do you do it, I prepared a few more slides to really explain what I'm doing here. So by swapping this FC layer with GAP layer, what I'm doing is I'm turning this FC layer into a one-by-one convolution. So I think for convolutional neural networks and also for semantic segmentation, it's a key trick to understand fully connected layer as one-by-one convolution. All right, so if you're applying your linear layer on top of a feature vector, then you can understand that as a fully connected layer or linear layer. But if you're applying the same set of weights, linear weights, on a feature map, where you're applying the weight identically to every feature location in the feature map, then that's exactly what one-by-one convolution is doing. And here, what's happening is you're doing one-by-one convolution on the original feature map, right? So yeah, you're doing dot products on every location H and W across the channel dimensions L. That's it. So, so what that means in practice is something like this. So visualize it. So let's say this is the original ResNet 50 architecture. So after the layer 4, you have output of size 2048 by 7 by 7, where 2048 is the number of channels. And then you do global average pooling to get 2048 dimensional feature vector. And then you have an FC layer of dimensions 1000 and 2048. And that eventually ends up with a 1000 dimensional prediction vector, logit vector. And afterwards you do softmax and cross entropy if you like. What CAM does on top of that is for this weight vector, you take the slice corresponding to the class of interest, Australopithecus, and then you are multiplying this vector. Yeah, it's a 2048 dimensional vector, right? With this feature vector. So you're doing broadcasted pointwise multiplication with this vector and this tensor, and then you're collapsing the channel dimension. And that gives you 7 by 7 feature map, where the channel dimension is not just 1. What I'm suggesting here is that instead of doing this, the original formulation here, you can do this adjusted formulation down there. So instead of doing FC layer on top of this feature vector, you can apply this fully connected weights on the feature map itself. And that's going to turn every single feature pixel here. There are 49 feature pixels here. Every single of them into 1000 dimensional vector. Okay, and then you can do global average pooling on top of that to eventually generate the logit values. And actually, these two are mathematically identical. And also in practice, they are identical. We also did some experiments around this. So if you train this network and this network, the result is completely identical. There are some numerical errors, of course, but yeah, they're the same architectures. And now, yeah, I would say this is like fully convolutional ResNet 50. So because just before the final prediction and global average pooling, everything is fully convolutional. So if you write down the model.py file, this is how it looks like. So you have layer 4, which gives you feature vector, feature map here. And the last convolution is also doing convolution. So you also have a feature map here. Then you do average pooling, and that's it for your network. So, for generating the CAM from this, what you can do is you just take the slice corresponding to the class of interest. And you don't need to do any weighted average. You don't need to take the weight vectors from the parameters. You just need to take the slice. Well, taking out the weight parameters and so on is generates some dirty code in PyTorch, right? Because you have to go into the dot data, dot blah blah, dot CPU, whatever, and then you have to take the matrix out, and that's not so clean. But in this case, you don't need to take out any of the weight matrix here. Just need to take the slice from the feature. And features are always exposed in PyTorch code or yeah, in many deep learning frameworks. So it's much better to just deal with features. But of course, you're using more memory actually here because you need to store this feature in the GPU memory. Whereas before, like you only had to store this vector here, right? So it's a bit more space, but compared to the whole size of the network, this is negligible, I'd say. So these are kind of diffs in the code when you modify this model.py file. And you can also transplant the weights from the FC layer into this one-by-one convolutional layer very easily. So even if you have some pre-trained ResNet-VT model according to the original formulation, you can easily turn this model into this one-by-one convolution or fully convolutional formulation just by transplanting the weights from the FC layer to this convolutional layer. So I'm just saying you don't need to retrain something, you just need to do transplantation. Okay, so that's the simplification. And here, let's take a look at what are the hidden assumptions for CAM to work. And let's try to see how far we can stretch the boundary of where CAM still works. We do not actually explain the first part of the network if we do this. So yeah, we kind of trust the score map to encode some pixel-wise information, right? And so when we do attribution to the score map here, by looking at the contribution like pixel-wise summation here, so what we do is we do upsampling of this 7x7 map to the original 200 and 200 by 200 input dimensions. And we kind of expect that every pixel here corresponds to the pixels in the original image. Well, this is a translation invariant or translation equivariant convolutional neural network. So there's a good reason why that should work, but we should also keep in mind that if you look at the the feature window or the how is it called? The field of view. I forgot the other word actually. The field of view for every single pixel in the feature score map. The field of view goes beyond the input image actually. So for determining the value here, every single pixel in the input image is contributing. So there's no clear-cut one-to-one or many-to-one segregation of input pixels to different feature spatial dimension here. So that's one big caveat. But still, we kind of trust that, yeah, for this pixel here, probably the corresponding region is contributing the most. So we do trust it. Yeah, but beyond convolutional neural networks, that's the question, is it going to work? So what about transformer architecture? So this is vision transformers, and how it looks like. So by the way, this is non-examinable. I'm just explaining. So this is the given image, and what you do is you dissect the image into different patches. And these patches are turned into tokens. And the way you turn them into tokens is by doing some linear mapping, right, for example. And you end up with some token here, and then you concatenate that with some positional encoding here, which is like a sinusoidal function. That does a full cycle across the feature locations. And you have a spatial token here, indicating, this is actually the token eventually where I'm going to get class relevant signal. And on top of this token, you're going to have some multi-layer perceptor and head to turn that into class prediction vector, 1000 dimensional. And transformer encoder here consists of some norm and multi-head attention, and then norm, and then multi-layer perceptron, and so on. So these are all repeated L times. So L is the number of layers for transformer. Now these patches seem to indicate some location in the image, right? And so, and the transformer is not decreasing or increasing the spatial dimension along the way. So the sequence length is always preserved across all the layers. So in other words, there's some nominal preservation of spatial dimensions. So can we expect that, yeah, the location here, the token value here, is representative of what's happening here, all right? So that's kind of natural for fully convolutional network, for example. But for transformers, this is not the case for two reasons. So one is the fact that eventually you're not doing global average pooling on top of these tokens. So, but you're actually taking only the zeroth location for making the prediction. So you're forcing the network to kind of aggregate all the information to this zeroth location across multiple iterations of these self-attention layers. So yeah, so there's no intrinsic meaning of location in this case. And if you look at the mechanism of self-attention, it turns out that yeah, so this is the input set of tokens. So each row here is a token, and n is the number of image patches. So every token is transformed into some query key and value. So yeah, every token is a row here again, and row here again, and row here again. So I'm not sure if you're familiar with self-attention mechanism, so it's not examinable anymore. So anyway, so I'm just gonna go super quickly here. Well, it should be n here as well, sorry, n here as well. And you take the matrix multiplication between these two. So you're gonna look at basically the similarity across all different possible pairs of patches. So this is gonna be like a similarity matrix for different patches, n by n matrix, distance matrix. And then you're gonna take softmax across the rows here. And that's gonna be a matrix where you know how to now take the values from the original matrix. So yeah, the takeaway here is that the computation here is across all patches of the input image. So there's no inherent preference for the current token to take information from the neighborhood of that location. But rather, this is like many-to-many kind of yeah, long-range dependencies. Like you do not prefer what's similar in the neighborhood of the patch. So there is no intrinsic preservation of information in each token location. So yeah, for transformer, it's not likely that CAM will work. Yes. Now let's summarize this part, feature attribution part. So we looked at two cases when you explain the entire model on a small neighborhood of test sample of interest, or you explain the whole input space for a small part of the model, like CAM. Okay. And for explaining a small part of the input space, we had two paradigms here. So one is response to local perturbations versus response to global perturbations. So far, any questions? Yes.
So one question to the original how to remove information for images. I was wondering how to train the network to recognize some people in a no information.
Yeah. Thank you for the question. And so for pixels, So typically, let's say you have a model that's taking raw pixel values as input. But as long as you're choosing the raw pixel values as the input space, every pixel values are kind of taken, and they all have some meaning, right? Even if like pink is not something that's arising naturally in general, but there are also birds with pink color, right? Um, so eventually, to really indicate what's missing, you need to introduce some new values. Um, it's not so easy with pixel values because it also has some kind of continuous meaning. So if you're choosing a value that's outside the range of 255, then that perhaps has some meaning. So it's RGB values, right? So when you set this missing value as 256, let's say, then that's very close to either R, G, or B, right? So it still has some meaning, right? A space that's conducive to this kind of setting is when you have discrete space, because then you can introduce new axes, right? Every discrete feature is a new axis, basically. And when you introduce a new axis, you can make it kind of independent of the existing features. So what could happen with images, for example, is by using vision transformers, because in vision transformers, you're kind of turning the image patches into the tokens, and tokens are now discretized. So um, in fact, there is some work on doing, it's called masked autoencoder. So if you know what BERT training is doing, it's basically trying to predict the masked tokens, right, at the output. So it's like an autoencoder structure where you take in a sequence of tokens with possible masked tokens everywhere, and then you try to predict the correct token for the masked tokens. And you can do the same with the images. So you can have from time to time some masked tokens, and then you try to in-paint basically this patch by choosing the right token for this patch. So for doing it right, doing the missingness representation right, I think you have to kind of go back to this or move to new paradigm of representing images, like first discretizing it and then doing something on top of it. Okay. Yes.
For the vision transformer,
Mhm.
is it possible or meaningful to highlight the attention score for each of the image patches? So to basically say, okay, there are 2 or 3 image patches that contributed a lot to the.
Yeah, so that's a great question. A lot of people do take a look at the self-attention, especially this post softmax values here, to see which tokens are contributing to which tokens. Or they can also take a look at some kind of summation across all these, because like the row here is basically the full image, and in fact this is like 4-dimensional tensor. So you have to take a slice of it to visualize it into a feature map. But here, the problem that I have is there are so many design choices here. For example, whether you're going to take the average here to generate a feature map, and also this is a multi-head attention, so you have like m different copies of this self-attention mechanism. So whether you wish to choose one of them using some logic, or you want to take the average of it. By the way, if you take the average, you don't generate some meaningful heat map anyway. So, and also it's not so clear how to interpret it, right? With CAM, we had a good understanding of, well, eventually the final prediction is made of the summation of all these pixels. But here we don't have that kind of intuitive interpretation of what's actually happening. So it's rather complex. I mean, the values are in the right range for humans to kind of explain, yeah, this is a softmax value between 0 and 1. but it's not easy to embed the value into some the mechanism. So yeah, so I have a lot of reservations against explaining something using self-attention values here. Yeah. But I should say this is an active area of research, how to explain vision transformers. And I feel like my impression is that people try to go back to um, another line of work in explainability, which is looking at different variants of backpropagation. So there's been something like activation, propagation, or something like that to turn backpropagation into some other uh, functions and relevance propagation. Yeah. But yeah, I should say I'm not a big fan of these methods. I'm not a big fan of many of the methods in explainability, by the way, because you know, yeah, I deleted the slides here, but they tend to be not very well defined in mathematics. So they are only defined in deep learning frameworks, but like for example, there are different ways of writing down the same function in deep learning framework. So even if the mathematical function is the same, there are different ways of representing it in code. And these relevance propagations tend to depend on the way you write it down in code. So even if the function is the same, depending on how you write it down in code, your explanation will be different. And I think that's not a good sign for explanation. So yeah, but people do look into these directions to explain transformers. But actually what I like the best in explainability paradigm is actually training data attribution. I wish to talk about it as well. Now, model is a function of training data as well, right? So instead of just looking at the test features, I wish to attribute the training samples. Okay, I think that's far more intuitive than looking at different features or looking at different parameters. Because training samples are really the ones that humans do understand. And we can perform actions on top of it, like removing training samples and so on. So yeah, I had some material here, but yeah, we covered that at some point. Explanation of model parameters, I wish to say a few words about that. So some people try to explain based on the model parameters as well, but I think fundamentally this is quite difficult. Depending on the model class, maybe this is possible, but yeah, sometimes it's really hard. Because model parameters are essentially millions of raw numbers. It's not even between 0 and 1, it's a real number. So it could be minus 100, it could be plus 1,000. What does that actually mean, right? We don't have any good understanding of what these values mean. So if you really wish to understand these parameters, eventually you have to project them onto some input space. And there are some non-examinable kind of slides to show what could be a possibility here. So there's been some attempt at turning parameters into samples. So eventually, to understand parameters, you still need to borrow the format of input samples for humans to actually understand it. So yeah, so for final weights of the network, you try to visualize that by coming up with some input that's kind of maximizing the output. Okay. Okay, so this is a quick examinable. So the reason why this is examinable is because it has certain similarities with the attack algorithm. So what you're trying to do here is to maximize the prediction score for class C for image I, and then yeah, you try to maximize it. So And you have some regularization here to make sure that your image is not going crazy. So its value should be kind of confined to some, some right range. And if you do that, then you have the visualization like this. So you can also try to maximize the activations as well in the intermediate layers, and you're going to see some patterns appearing. But one thing that I don't really like about this line of work is that it's mostly qualitative, so there's a lot of cherry picking going on. So you don't always see those nice pictures. Yeah, so these are more well known, right? So convolutional filters are essentially Gabor filters, people say, right? Which are trying to detect this kind of edge or some color changes and so on, or just single color like this one. Yeah. There are some other visualization techniques. So, by the way, if you put this into a neural network, then it predicts with high confidence that this is a king penguin, starfish, and so on. So, yeah, these are, I would say, adversarial examples as well. So there are certain similarities between adversarial example generation and this kind of model understanding. Yeah. So these are MNIST digits, 0, 1, 2, 3, 4, right? So more in this link. So if you're interested, you can take a look. So let's come back to training data attribution. Again, yeah, model is a function of training samples. So here, the kind of counterfactual question that I wish to ask is, what happens if you remove some training samples? So this is the original data set, and so always there's a pair, right? So there's a training sample, Z, written as the pair of X and Y, but there's also a test sample, Z. Sorry, it's Z here. So I always write Z for the combination of X and Y, the input and label. So I wish to look at the contribution of Zj, which is the training sample, on the prediction of test sample Z. Okay, so I write down the subscript here to indicate this is a training sample, and if there's no subscript, then it's a test sample. Okay, so this is a test sample. Let's say by removing this single sample Zj, you're decreasing the loss value for that for Z by 0.004. Okay, we are interested in this kind of relationship. What's going to happen to my test sample when you remove some training sample? Why is that important? Because that gives me some actionable guidance whether to exclude some sample or include some sample, right? Let's say we had some problem with the prediction of 7 in some cases. So let's say this is a test image and this was labeled as 7. Well, original label is 7, but you're predicting that as 1, let's say, or the other way around. And you found it super weird, and you try to find a training sample that's kind of critical for the prediction. And it turns out this one is contributing quite a bit to the prediction of this image as 7. Okay, I was a bit confused. So the original label is 7 here, but the prediction is 1, let's say here. Okay, and this is the harmful training image, meaning that, yeah, this is, during training, you see that this is a 7, and perhaps indicating this as a 7 gives a strong kind of bias for the model to say, yeah, this is very different from this image, so this is probably not 7, right? So by understanding what training samples are contributing to most to the current sample, you can actually decide whether to fix the sample or fix the training sample or do something on top of it. In practice, as engineers work with some training data, it's very important for them to understand what kind of actions they can take to improve the model in the way that you like. So let's come back to these 3 steps of XAI, approaching XAI problems. So first one is to identify a few real-world problems, and two is to identify a well-defined task which is going to help with a lot of real-world cases. And three is to introduce some approximation of two, because most likely two will be very expensive. And we're going to see that for training data attribution, the step two is actually unreasonably expensive, because, yeah, you're going to see. So there are some real-world problems related to training data attribution, TDA in short. There could be some cases like the model behaves weirdly on some sample, or I wish to fix the issue by improving the training data set, by removing certain samples or increasing, like including some more samples. Or sometimes you're interested in identifying, let's say for a generative model, right, like language models, it generates some sentences, and you wish to know whether by copying and pasting this sentence to my creative work, am I infringing upon anyone's copyright? Or am I actually making use of some private information of someone else? And for that, we also need to kind of attribute the current generation to some previous, some training samples. So for that as well, we need some TDA approach. And there comes many variations to this problem, whether to focus on a single test sample or multiple test samples, okay? Whether you want to fix the behavior of the model on a very specific case or a group of cases, or for the entire set. There can be different actions, right? You can try to remove some samples, add some samples, relabel some of the samples, or reweight some of the samples. And likewise, for training samples, we can fix just a single training sample or multiple of them. Okay. So I'm going to talk about the most popular task here, which is leave one out retraining. So here the question is, what's going to happen for this particular test case of interest when you remove a single training sample? And by doing this, we can kind of rank the training samples in the order of importance for the prediction of the current test sample. It's also assigned a value, so the rank will give you on top of the list the most helpful sample for making the current prediction. And on the final end of the list, you're going to see most harmful cases, meaning that, okay, so if you remove the most helpful cases, then you're going to see the test loss increasing. And if you remove the most harmful cases, then you'll see that the test loss for this case will decrease. Because if you remove harmful ones, then your model should improve on this sample, right? So that's leave one out retraining. I write LAO in short. Yeah, so this is a counterfactual question. And this is very expensive, right? Because if you wish to compute the true effect of removing Zj on some test sample Z, well, I wish to write Z here instead of X, then you have to do several computations. So first of all, you have to perhaps train more than once, right? Because actually for many neural network training, the training procedure is stochastic. So in order to identify the true mean and variance, you need to train it multiple times. So that's T, right? And also in practice, you're interested in finding the most important, most contributing training sample in your training set. So you have to do the retraining for the number of samples in your training set, 1 million, right? And let's say that's N. And you might also be interested in the impact on several test cases. And let's say we're interested in M test samples. And that gives you T times N times M model retraining. And that's very expensive, right? So there we need some approximation. And TDA methods are basically, the question is how to approximate this expensive procedure. So for that, we need to look at soundness and efficiency at the same time as before. Okay, and we'll continue from this evaluation next time. And here's the final slide for your feedback.